We did our video project on the application of biogas. The production and use of biogas is a green engineering application that provides great potential for sustainable energy. Biogas is generated through the use of anaerobic digestion. Microorganisms break down biodegradable materials, such as food, into carbon dioxide and methane. Methane can then be used to generate energy for consumer use. The problem: 80% of the water and 50% of the land in the United States is used in agricultural production. 40% of the food that is produced is never consumed, and an estimated 70 billion pounds of food is wasted each year. This wasted food is sometimes fed to livestock, left in the fields to rot, or even directly hauled to the landfills. Growing trash concerns. The world is expected to produce 2.6 trillion tons of trash this year. To put that into perspective, that is the equivalent of 7,000 Empire State Buildings in weight. We are facing challenges regarding the disposal of trash. Currently, we put most of our trash in landfills, while third world countries dispose of their waste by dumping it into their waterways. This can be very troubling since they could potentially be contaminating their water sources. Technical data and analysis. In the United States, we have the potential to produce 2.5 million tons of methane each year, just from landfills. The average energy density of methane is around 50 megajoules per kilogram. In 2015, the average household energy usage was around 10,812 kilowatt hours per year. We did a simple calculation to determine how much energy could be produced from the volume of annual waste that we produce. Engineering issues and considerations. For the feeding process, initial testing must be done. These tests include solid moisture content, chemical oxygen demand, and biochemical methane potential. For preparation, the food waste must be grinded, and a ratio of 10 to 25% must be achieved for the solid and water ratio. For digester conditions, the pH should roughly be around 7, while thermophilic must be grown in 50 to 60 degrees Celsius, and mesophilic must be grown in 35 to 40 degrees Celsius, and temperature control is also required. For gas filtration, the removal of hydrogen sulfide, water, and CO2 must be achieved. This is achieved through water scrubbing, membrane separation, steel wool, and condensate traps. For gas storage, low pressure must be achieved, and this can be achieved through floating covers, gas bags, and water sealed gas holders. The uses include fuel for power generation and boilers, and upgraded biogas, which is used in natural gas pipelines. Some of the pros and cons include carbon neutral power generation, power production from waste, reduction of cost and emissions, nutrient-rich byproducts which are used for fertilizers, and the fact that it is stored as gas, which erases the need for batteries. Some of the cons include the fact that there is more water used and is less sustainable. Natural gas piping may require additional regulations. The non-methane part of the biogas can be harmful for the environment. Methane tends to be highly explosive, and additional energy is required to maintain conditions. Conclusion. Finally, the biggest concern with the implementation of biogas as a useful form of alternative energy is whether or not it covers all three components of the triple bottom line. From an environmental perspective, cutting back on the amount of waste through the use of biogas will help clean up the environment. This in turn will create social prosperity. The hardest component of the triple bottom line is concerned with economics. The process of creating biogas is relatively cheap compared and requires minimal capital investment to other forms of energy production. Furthermore, the implementation will also allow for an influx of new jobs, which in turn will help stimulate the economy.